you look at the Fourier series frequency spectrum, maybe let's go back to the previous chapter one more time. Okay, we have to go back to the chapter 4, coming back and forth many times. That's fine. If you look at those fingers, let me turn up the. See, these are the discrete frequencies. 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0. These are the discrete frequencies. The frequency response always occurs at those discrete frequencies. 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0, and so on and so forth. Okay? So let's define omega n. I'm going to show you the omega n and omega 0. Okay, so the distance between omega 0 to 2 omega 0 is omega 0. These are distance. Now you can imagine when this T0 becomes bigger and bigger and bigger. Okay, when the period becomes bigger and bigger and bigger, this number becomes smaller, smaller, and smaller. Okay? So let me call this delta omega. So we are going to call this delta omega. And similarly for this is delta omega. Okay, so this and omega, sorry. N 2i over t sub 0. And we are going to define this distance, okay, for the integral, plus the fundamental frequency. And that will approaches 0 plus T sub 0 approaches infinity. So you can see that the interval becomes smaller, 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 and smaller. This is also a delta omega as well. Okay, so that's the point. This is the tricky part. This is the tricky part. Okay? Alright, so the Fourier series expansion of the periodic function now can be written in this way. Okay? So again, this x of omega n is t of t sub 0 times xn. T sub 0 times xn, so t sub 0 cancel out this t sub 0. We'll go back to the expansion. Actually, I understand up to this moment. Okay? This is equivalent to this one. But we'll just define another function called x of omega sub n. That's fine. Okay, and then the t sub 0 this time. Okay, this t sub 0 now can be replaced by delta omega over 2 pi. Okay, delta omega is 2 pi over t sub 0. Okay, so 1 over t sub 0 is equal to delta omega over 2 pi. just a direct substitute. Okay. All right, and then this x of omega sub n, x of omega sub n, now is given by this one. 1 over this, okay, originally is here. Yeah, up to here. Okay. Up to here. This n omega sub 0 now is replaced by omega sub n. Replaced by omega sub n. But we don't have 1 over t sub 0. Okay, that's a twist. That is a twist. But basically, we don't do anything except that we kind of multiply, the x sub n by t sub 0. Okay, so that's why you don't see the t sub 0 over here. Okay. All right, and then we let t sub 0, the fundamental frequency, go to infinity. We assume the function has infinite period of time. That's a tricky part, that's the idea. Then this delta omega can be replaced by d omega, becomes a very teeny tiny small quantity. Okay? Then in this case, this function x of delta, x delta of t now can be changed to x of t because here we, by definition, x of t is the limiting process of x delta of t when t sub 0 go to infinity. Okay? So this x delta of t now can be replaced by x of t, and then the right hand side, the summation, now can be replaced by integration. This can be replaced by integration. Where's the pen? Okay, whatever, I cannot find a pen, sorry about this. Alright, anyway. So this summation now can be replaced by integration. And delta omega now is replaced by d omega. Okay? So x of t now becomes 1 over 2 pi times the integration. Actually, this is projection. Okay, it's a projection. Okay? And the coefficient, x of omega, now is a function of omega, and this omega is a continuous function of the frequency, not discrete frequency anymore. Okay, and this frequency component is given by the projection of the time function x of t on this complex exponential function. It's a projection, okay? Similar to the Fourier series expansion, except that the period t sub 0 goes to infinity, So we use the periodic function to approximate a non-periodic function. We call that aperiodic. Okay, we call that aperiodic function. Okay? And then we have the Fourier series transform. And then we have this Fourier series transform. Got it? Okay? So the frequency component, x of omega, is the time function projected onto the complex exponential function. And actually this complex exponential function has two components. One is the real part, the sine omega t, and then this is minus, right? So negative a sine omega t. So So it's a projection onto those sinusoidal functions, right? Okay. Well, any question up to this moment? Any question here? Suppose we have a rectangular function, a rectangular function, trend. Okay, so it is a periodic function. We have many, this kind of rectangular function. The period is, this is 1 second, 2 seconds, right? 2 seconds. So we start from the fundamental period, 2 seconds. And if we perform the Fourier series expansion, this will be the magnitude of the Fourier series expansion. And you can see that the frequency component occurs at discrete frequency. 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0, negative 1 omega 0, negative 2 omega 0, negative 3 omega 0. Now if we increase the period, t sub 0, okay, we increase the t, the frequency on the fundamental period, then you will see the frequency response. The shape are quite similar. But the gap, okay, the interval between the frequency components becomes closer and closer and closer. Okay? When eventually the period approaches infinity, then these frequency component becomes 1 next to 1. Okay? It becomes very, very, very close. It becomes eventually a continuous function in the frequency domain. Okay? So that's the basic idea. We start from Fourier series expansion with finite period, and then we let the period become bigger and bigger and bigger and bigger. Then eventually this function actually is not periodic anymore. Okay, limit t approaches infinity. Then the corresponding Fourier series expansion now becomes the Fourier transform. And the frequency response actually now is a function of t continuous frequency in continuous frequency domain. This is discrete frequency. Now this becomes continuous frequency. Okay? That is a big difference. But they are similar. You can see that. They are similar. Okay? Question? Well, any question up to this one? Any question up to this one? Okay? Okay, let's skip this for a moment. Mathematically, let's assume we all are dealing with inequitable function. Okay, now here is a very interesting function that let me start. Okay, so let's just go through the result. Suppose we have a unit step function. Next one of t is u of t. It is a unit step function. It is, okay, this unit step function is not periodic, right? It is not periodic. Be careful. Now, if I try to take the Fourier transform of this unit step function, okay, there's a mistake in the book for this example. Okay, but definitely it is the correct answer. Okay, but in this book, please make a correction here. It says that this Fourier transform cannot be 10. It is incorrect. And actually, the Fourier transform of this unit step function, okay, is given by high the impulse response delta at 0 plus 1 over j delta. Now, the way we derive this is to replace this unit step function. Okay, originally it was still be solid. Originally, we defined the unit step function of t as the function value is 0 when t is smaller than 0. The function value is 1 when t is bigger than or equal to 0. Okay? But in order to be integrable for the Fourier transform, we add one midpoint at the 0. So we change this, we modify this to when t is smaller than 0, u of t is 0. But when t is equal to 0, u of t is 1 half. When t is bigger than 0, u of t is 1. So we have a midpoint. So here we have a midpoint. Oops, sorry. Okay, so originally this is not t. No midpoint. It's a discontinuity. But then for the purpose of the function, of integrable function, we add one midpoint. Okay, but due to that modification, we are able to find the Fourier transform of u of t, of this u of t, and it is equal to pi times the impulse response, pi times the impulse response, plus 1 over j omega, 1 over j omega, okay? So, because it is subtle, so I think I gave you, what else? It seems I have uploaded. Oh, not yet. I will upload that. There is a paper discussing the Fourier transform of unit step function in very detail, but it's too involved, so I'm not going to discuss the problem over here. Okay? So just want to show you that this statement in the book, okay, must be modified. There is a Fourier transform for the unit step function if we add the midpoint over there. Okay. Okay, let's go back here. So once we modify the unit step function like this, then the unit step function can be replaced by 1/2 times 1 plus the sine function of t. Okay, so this function now can be replaced by, or equivalent to 1/2 times 1 plus sine function of t. Okay, what is sine function? Negative. T is smaller than 0, equal to 0. When t is equal, positive. When t is bigger than 0. So the unit step function can be replaced by 1 plus the sine function. And you see that negative, positive, and 0 for here. Okay, so once you add entire side multiplied by 1, so this becomes 0 and then 2. And then we divide by 1/2. We have this. Okay. So this is 0 again. And this is 2. So now we have midpoint at 0.5. This we adjust when t is smaller than 0 is 1. Okay, and 1/2. When t is 0, and then negative. Sorry. This is 0, and this is 1. Okay. So we make this kind of modification by adding 1 midpoint. All right, so that's the Fourier transform of the unit step function. Okay, and then eventually it looks like this. A kind of L shape, but there's a spike at the center, which is at omega equals 0 frequency. Okay. All right. And actually, this Fourier transform can also be obtained from the Laplace transform if we are dealing with one-sided signal or total signal. Okay, for example, like this: x of t is given by e to the negative 2t times the unit step function. So here we just consider the positive term. Okay, when t is bigger than or equals to 0. So we can have the one-sided Laplace transform. X of s is equal to 1 over x plus 2. 1 over x plus 2. And in this case, its Fourier transform is simply 1 over x plus 2, but replace this by j omega. Okay? So we just consider the frequency at the j omega axis. So it becomes 1 over j omega plus 2. Now, if we consider this function, f3 of t is equal to e to the negative, the absolute function of t. Now here, actually we are considering two-sided Laplace transform. Two-sided Laplace transform. So this part is for the causal part, and this is for the non-causal part. And we have to add them together because for this case, we are dealing with two-sided Laplace transform. Sorry, times e to the negative 2. E to the negative 2 times. Yeah. Okay. So this So we are going to divide it into two parts. Okay, from 0, and then 0 to 15. Actually, this is still fine. So this is e to the negative. So this is negative t. Okay, so we have to divide it into the two parts. So one of this guy will give you 1 over x plus 1. And this guy, first one, will give you 1 over negative x plus 1. Okay, to try to see what happens. All right, let me give you a little bit of detail here. So, so now you are going to apply the Fourier transform. So you can divide this into two parts. Okay, and then this can be, for the moment, we can put it into the negative 3. And then absolute function here. Negative. Absolute. Okay, now for t is negative. For t is negative. This value must be always negative, okay? So for t is negative, so I can replace this by e to the t, right? For t is negative, this number is always, for t is positive, this is always negative, so this is negative. So that's why. So I put it on this side. And then you repeat that again. So originally this is e to the negative absolute function of t. This is negative absolute function of t, right? And you turn over. So look at this exponent here. This is always negative, except t equals 0, or smaller than or equals to 0. Okay? So for the negative t, I can simply replace this by t, because this time t is always smaller than or equals to 0. Okay? And similarly for this one, again, this is always negative or equals to 0. For t is positive, and this is negative. Okay? That's why I write this as positive t, and this is negative t. Okay? So if you integrate this function, you should be able to find replace this by negative this. cell, initial cell is correct, okay? So for this function, the Fourier transform actually can be reclaimed from the two-sided Laplace transform, and replace the complex frequency S by j omega. Okay? So now we have the Fourier transform of the function. 2 over 1 plus omega squared. Okay. Any question up to this moment? All right. Now, this Fourier transform also is a linear function. Okay, it's a linear operator, and then the way to prove it is very straightforward. So let's assume I have two functions, x of t and v of t, and the Fourier transform of f of t is x of omega. The Fourier transform of v of t is v of omega. And then we are going to show you that if I have a linear combination of x of t and v of t, so I have a times x of t plus b times v of t. Now a and b, they are scalars. They are two scalars. And they are two scalars. Can be real number, can be complex number. That's fine. And the Fourier transform of this function, a times x of t plus b times v of t, is simply a times x of omega plus b times v of omega. Okay? So the proof is straightforward. So this define y of t as a times x of t plus b times v of t, and plug it into the Fourier transform. So we replace y of t by a x plus bv, and then we split these two functions. And then we have a times x of omega. This is the Fourier transform of x of t, and b times v of omega. This is the Fourier transform of v of t. Now, there's a catch here. It looks okay. Looks fine, right? But be careful. Mathematically, there's a catch. We assume this can be split. Okay? By assuming that actually we are dealing with a finite function, x of t and v of t both are finite functions. If one of them is empty function, well, we have a problem. Okay? So that's a mathematical issue. We are not going to discuss that. And practically, we don't see that kind of situation in engineering problem. Okay? Except for some extreme cases. So let's assume this can be done. So I can split these two functions into two integration. Okay, let's assume this is doable. But again, let me warn you. Whenever you are going to split a function in the integral, be careful. You have to make sure that this can be done. Because if one of them is, say, infinity, okay, and this is also another one, but with a positive answer, with an opposite sign, then you have a problem. You have positive infinity minus another infinity, okay? There's a problem here, there's an issue here. We don't want to discuss that. Okay, so let's assume, well, there's no problem here. We are dealing with good signals, good functions, okay? So no problem at all, presumably. So Fourier transform is a linear function, here. Okay, then the next property is the inverse proportionality of time and the frequency. And actually, this is similar to the Laplace transform. Let's take a look at Laplace transform. In the Laplace transform, I think you all have seen this one. Expansion and contraction. F of alpha t, if you take Laplace transform of this function, okay, now you either expand or contract the function. The corresponding Laplace transform becomes 1 over alpha times Laplace transform. It should be Laplace transform, sorry. There are this. My mistake. Yeah. Okay, whatever. So this is the Laplace transform of the function f of t. Okay, so the Laplace transform of this function now becomes 1 over alpha times the Laplace transform of s over alpha. So in the function, you multiply it by alpha in the time domain. Okay, for the function in the time domain, if you multiply it by alpha, then in the frequency domain, you multiply it by 1 over alpha. What does that supposed to mean? Okay, let's look at the example in the Fourier transform. Maybe it's much better. Okay, this is one example taken from the book directly. Look at the figure on the left side. Suppose this is the x1 of t. Okay? And then this is the corresponding frequency response to the Fourier transform of this function. Okay? Now if I multiply t by 1/4, actually extend the function. So I stretch the function. So this function now becomes wider, right? It becomes wider. Anything on in there, right? So I stretch the function. So the function becomes flatter, becomes wider and flatter. And if you look at the corresponding Fourier transform, the frequency response, the frequency response much more concentrated at the center. What is the center? Zero frequency. Okay? And look at this one here. The frequency distribution becomes much more even and wider. Okay? And then for this one, the frequency response concentrated, most of the frequency response concentrated in the neighborhood of 0. So this means the major frequency component of this guy is it's very similar to 0 frequencies, a constant, which is a constant actually. Okay? So this is much more like a constant function, 0 frequencies. But for this one, think about this in the limiting process. When the period becomes, when the width becomes very, very small, very, very narrow, it goes to kind of impulse, okay? And then for the impulse, the corresponding Fourier transform will be a constant, which means we need many high frequency components, many high frequency components to approximate or to construct this impulse function. Got it? That's a major point. Okay? So one more time, let me say that again. If you stretch this function, it becomes much wider, becomes much more like a constant. And the frequency component or constant majorly concentrate at 0 frequency. That makes sense. Okay? And for a delta function, when the width of this function becomes very, very narrow, this can be thought, okay, can be approximated by an impulse function. For an impulse function, the frequency component becomes almost like a constant, which means we need many high frequency components, many high frequency components to construct the impulse response, to construct the impulse response. Okay? So that's the point you have to know, all right? Okay, let's take a break. 10 minutes break, okay? All right, yeah, feel free to take a break. Okay, think about this. If you have questions, let me know later on. Okay, suppose we have x of p and the corresponding Fourier transform is capital X of omega. Now, if we multiply p by r, so by a or by r, so either we stretch or compress the function, and we call that y of t. So we are going to show that the corresponding Fourier transform, y of omega, will be 1 over a times x of omega over a. Okay? So the Fourier transform of y is given by definition, y of t times e to the negative j omega t dt. And this y of t now is replaced by x of a dt. Okay? And then we define another new variable in the time domain, t prime equals a times t. So this exponential function can be written as negative j omega times t prime over a times the omega prime over a. Okay? And then we can bring this constant 1 over a out of the integration. And this integral, indeed, this one, is the Fourier transform of x at the frequency omega over a. And that's it. So the proof is straightforward. The proof is straightforward. Okay? All right. So that is the proof. Okay? Okay, what's else? Okay, in the time domain, if we shift the time, that means if we delay or advance the time, then in the frequency domain, it is multiplied by negative j omega times c. Okay, c is the time you delay or advance. Okay, again, the proof is very similar to the Laplace transform. Okay, so let's do this. Okay. By the way, I will show you the. I will give you the slide later on. Okay, I will give you the slide later on like I did before. So don't worry about this. Okay. Okay. So here comes the interesting part. Duality. Okay. Now let's read this for. Let me read this for you first. Suppose I have a function x of t, and its Fourier transform is x of omega. Okay? Now, if I replace the time function x of t by its frequency component, capital of t, and then the frequency response, the Fourier transform, or the frequency response of this function is simply the time function. I replace t by negative omega multiplied by 2 pi. Very strange. I mean, very surprise. Not strange. Surprise, okay? So what does that tell us? What does that tell us? Look at this figure here. Suppose I have an impulse function in the time domain. Then its Fourier transform is a constant 1. It's a constant 1. Alternatively, if in a time function, okay, is 1. If the time function is 1, then the associated Fourier transform will be a delta function multiplied by 2 pi. Okay? Very, very interesting. A delta function mapped to a constant. A constant mapped to a delta function. So So that's a duality here. Okay? You will see lots of this kind of phenomena in the Fourier transform. That's a very interesting result. Okay, another one, let me show you that. Yeah, okay, let me see. Let's see this for a moment, okay? Okay, maybe let's go to the proof first. And then go to the proof first. Yeah, here. Okay, suppose I have a function x of t in a time domain, and this is the corresponding Fourier transform given by the integral of this function, x of t times e to the negative j omega t. And then the inverse Fourier transform is given by 1 over 2 pi times the integral of x of omega. Okay, this guy is the frequency component times e to the j omega t dt. Okay? Now, if I multiply this function by 2 pi and replace the omega. Replace t by negative omega. Okay, one more time. Let's multiply this function by 2 pi and then replace the t by negative omega. Okay? So this multiply by 2, if this multiply by 2t this time. 1 over 2 pi times 2 pi now becomes 1. Okay, and then maybe let me restart the screen. Sorry. Here for the moment. So the frequency component is a projection. In the time domain, but I'm going to change the down variable first. Okay, this how can be any down variable. So if I call this rho, then I just make the heat at the rho. The results still the same. You see that? result is still the same. I can change the name, whatever I need, whatever I want. So nullify the function by 2 pi, and then change the argument from t. Back to the t. Okay, I'm sorry, I made a mistake here, sorry. Hold on. I made a mistake, sorry. Okay, sorry about this. I forgot this. Omega t here. Yeah, here omega t omega. That's right. This is the omega, not dt. Sorry about this. Dt is this one. I forgot this. I made a mistake with this, right? So let me correct this. And this is the omega. Okay, sorry. Okay, for the moment, let me repeat that again. So this omega is the dummy variable, not t, sorry. Give me, I made a mistake. Okay, so this is the dummy variable. Omega is the dummy variable. Okay? And I can call that whatever I want. So let me replace it by rho. Okay? So now the omega, the frequency, now is replaced by another variable, say rho. Okay, so let me duplicate it here. So this makes out t is 1 over 2 pi n from negative infinity to infinity. X of rho e to the k rho t below. Okay? And then let's multiply the entire function by 2 pi. Okay? So now I have 2 pi times x of t is equal to the integral of x rho e to j rho t to rho. Rho now represents the frequency. Okay? Now, what if I change the argument? T, I replace the argument t by something else. Let me call it negative omega. Then I also can change t over here by negative omega. So now the argument t now is replaced by negative omega. And then look at this. What is this? This is indeed the Fourier transform. You look at the form of the Fourier transform of x of rho. Okay, for x of omega. Which will be x of t. Fourier transform x of t. Maybe this shows So I just bring the dummy variable back to T again. And that's a Fourier transform of this capital X of T. And again, capital X of T indeed is the frequency component, frequency response of the signal X of T. So if you take the Fourier transform of the frequency response, that will bring you back to the time domain X of T, will bring you the function X of T. Okay, all right. Okay, another important function we have to know is the cosine function, the sinusoidal function. Okay, the Fourier transform. The Fourier transform of a cosine function equals to the sum of two impulse functions. Where does that come from? At first, we rewrite the cosine omega t by the sum of e to the j omega t and e to the negative j omega t and divided by 2. We have the mean value of the two functions. Okay, and then take the Fourier transform of this time. Then you have two terms. And the first one is indeed the Fourier transform of this exponential j omega t. And the second one is the Fourier transform of this negative, Fourier transform of this negative, e to the negative j omega t, right? Okay, so it's a sum of two Fourier transforms of the exponential functions. And it is very interesting, if you take the Fourier transform of this complex exponential function, you will have the delta function. And this is where your homework assignment. Why? Okay? Show that, prove that the Fourier transform of this complex exponential function equals to the delta function with a shift in frequency times 2 pi. And similarly for this one. The Fourier transform of this complex exponential function with minus sign here. This is negative frequency. Then is equal to the delta function with the frequency shift, negative omega 0, and multiplied by 2 pi. Okay? Got it? Alright? Find the book. Find the book. See, how do we get this? Why the Fourier transform of this function is the delta function? And why this Fourier transform is also a delta function with the frequency shift. Okay? That's your homework assignment for this week. Okay? All right, so the duality property, we can use this figure to illustrate this property is given by this interesting figure here. Suppose I have a function, let me call it x of t. And the Fourier transform of the function is given by this x of omega, supposedly. Okay? Please do not argue with me. Well, this is not real, the Fourier transform of this one. Let's assume it is. Okay? So let's assume this is the Fourier transform of this function x of t. So this is x of omega. Now if I bring this function to the time domain, so this becomes x of t, right? And then if I take the Fourier transform of this function, then it turns out that, well, its corresponding Fourier transform will be 6 similar to this one, with a slight difference in the frequency domain. To flip the function in the frequency domain. But the shape are the same, except there's a 2 pi multiplier 2 pi. Okay? That's a very interesting result. That's the duality of the Fourier transform. Duality of the Fourier transform. Okay? Got it? Alright? Okay. So keep that in mind. That's a very important property. Modulation. Now, we have seen this one in the previous series. There was another one similar to the result. To the example we have seen in the series expansion. So let's take a look here again. Okay, now suppose I have the message. Okay, this is the message. Signal x of t. Now, if it is multiplied by a carrier, the sinusoidal function, e to the j omega 0 times t, then the modulated signal is given by this one. Okay, so this is a x of t multiplied by a sinusoidal function, e to the j omega 0, e to the j omega 0 times t. So this is the modulated signal. Then its corresponding Fourier transform, or the frequency response, will be a shift, a frequency shift, omega sub 0. Okay? The same shift of the original signal with a frequency shift, omega sub 0. So if this is the frequency response of, sorry, so if this is the frequency response of the original signal, this is the signal message, and this is the frequency response. Okay? Then once you multiply by the sinusoidal signal, this becomes a modulated signal. Then its frequency response will be similar to this one, but with a shift. So it becomes 1/2 of omega x of omega minus omega 0. This is this one, and plus another one. This is a positive frequency shift, and this is a negative frequency shift. So we split, we bring this into 2 parts due to the carrier, e to the j omega sub 0 times t. And this is identical to what we have seen in Fourier transform. Fourier series expansion. Fourier series expansion. The same. And one thing you have to see is, if you look at the amplitude, for the original signal, the peak value is 2. This is the peak value of the frequency response of the original signal. Okay? Original signal, the message. But once you modulated that, because you split the signal, your frequency response now becomes 2 parts, okay? So you can see that the peak value also divided by 2. This is 2. The peak value here is 2. But now the peak value for this one is 1, and this one is also 1. So it is split into 2 parts. And the power also is split into 2 parts, even. So this is the modulation. Okay? The same as the Fourier series expansion. Okay. All right. Okay, now in the beginning we said that the Fourier transform is for aperiodic or non-periodic signal. Okay, but what about if we are dealing with periodic signals? Fine. Then we may use the Fourier series. Fourier series expansion for the periodic signal. So suppose we have x of t, and its corresponding Fourier series is given by summation x of k times the complex exponential function e to the k omega sub 0 times t. Now if I take this function into the Fourier transform, I have the corresponding Fourier transform x of omega. And then this Fourier transform will be summation 2 pi times x of k is the Fourier series equation, and times the delta function with the frequency shift. Okay, with the frequency shift k times omega sub 0 shift. Okay. So here, that's why I need you to prove the Fourier transform of this complex exponential function is a delta function. It's an impulse. Okay? Confirm yourself. It is correct. So here is a quick example. Suppose I have a periodic signal, x of t. And I have another function x1 given by this guy. Okay. Alright, and then the fundamental frequency is this one. So, I think this is the previous. Okay, so let's take. So now if I use the Laplace transform directly to the x1 and to this one. Now this is the ramp. This is the ramp with time delay, and this is the ramp with another time delay. And let's assume the fundamental frequency is 2 pi. So we repeat this in every 2 pi, okay? Okay, so let's take the Laplace transform of x of 1 of t first. Okay, this is the ramp, unit ramp. So the Laplace transform is 1 over this square. And this is unit ramp with the time delay. So you have to multiply the output by e to the negative 0.5s. This is due to the time delay, 0.5 second delay. Okay? And this is another ramp, but there is a 1 second delay. So I have to multiply 1 over s squared by e to the negative s. So the Laplace transform of this x1 of t is given by this function. Okay, and you can summarize, you can simplify the expression if you want. Okay? So the Fourier transform, or Fourier series first. Fourier series coefficient first. X of k will be the x1 of s, and replace s by the discrete frequency k, j times 2 pi times k. Okay, this is discrete frequency. Omega 0 is 2 pi, so k times 2 pi, that is the frequency at discrete time, or discrete frequency. 1 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0, and so and so. Okay? So replace this by j times 2 pi times k. Okay, and that will give you the coefficient x of k first. And then the function. The Fourier transform of this function, periodic function, would be simply x of omega, okay, equals dimension 2 pi times x of k, suppose we have found x of k, okay, and then times the Euler function, times the Euler function, and then sum up over here. Now, there is a catch here, careful. When k equals 0, we have a discontinuity, we have a singularity. So we want to divide it into two parts. One is for k equals 0. Another one is for k equals non-zero. Okay? For k equals 0, what is that? K equals 0. What will happen? What is x of 0? What is x of 0? When you are computing the Fourier series extension. What is the coefficient x of 0? Let's go back to the Fourier series again. This is kind of fundamental concept. Okay, so let's go back to Fourier series again. Fourier series here. Yeah, that's fine. This one's fine. Okay, now if k is 0, k is 0, this is 1, right? So this becomes the integral of this x of t in the interval, in the periodic interval, t sub 0 to t sub 0 plus t 0. You can assume t sub 0 is 0. Okay, so from 0 to capital T sub 0, 1 period. So the x of 0 actually is the mean value for the function in 1 period. Mean value, because it also divided by the interval t sub 0 period. So x of 0, actually that is the mean value of the function x of t, okay, in 1 interval. Alright? Yeah, I mean something. So when k is 0, for this case, you have to find out what is the mean value for x1 of t in the interval. Omega sub 0 is 2 pi, so t sub 0 is 1 second. So I have to find out the mean value of this function in 1 second. That will give you x sub 0. Okay? Got it? X of 0 was the mean value. Okay? So we have to find out the mean value of the function x1. In this case, that's this x1. That's 1 period. Okay. Oh yeah, it is in figured out. In the beginning, 0.5. Confirm that by yourself. Confirm that. Okay, if you want to take it. can do that here. So that is x equals 0. That's 1 over 2t, 1 over t0, excuse me. R of t minus times R of t minus 1 plus R of t minus 1. Okay, confirm this by yourself and make sure you know that it's true. Okay, so this is the example. Okay. Alright, so this one is skip that for a moment. Okay, let's move to the next one. Symmetry of spectral representation. Now, in the beginning, we know that suppose we have x of t, we have a function x of t, then the corresponding Fourier transform is by the integral x of t times e to the negative j omega t dt. Okay, so actually that's a projection of the function of x of t onto the complex exponential function. So this x of omega, the frequency response, can be decomposed into two parts. One is the real part, one is the imaginary part. And sometimes it is sometimes also written as the magnitude times the e to the j times the angle, phase angle. Okay, this is the magnitude, absolute value of x of omega. And then times the phase angle. Sorry, what's this? E to the j times the angle of x of omega, right? And usually we use this expression in the body plot. They will sketch the magnitude and also the phase angle. This is called the body plot, frequency response. And we can show that if we are dealing with the real function x of t, then the magnitude of the Fourier transform is a symmetric function in the frequency domain. Okay, so the absolute value of x of omega is equal to the absolute value of x of negative omega. So this means the real part, if you look at the real part, it's even function in the frequency domain. And if you look at the imaginary part, then it becomes an odd function. It becomes an odd function. Okay, and similarly, the phase angle is also an odd function. All right, now the proof. We can see that the proof. If we define the frequency response the way we showed here, then the x of t is the inverse Fourier transform of x of omega, is given by this integral. Okay? Now, if I take the complex conjugate x star of t, then I take complex conjugate over the entire integral. So the first function becomes x star of omega. The second exponential function becomes e to the negative j omega t. Right? We take the complex conjugate over the product of the two functions. Okay, so this is the inverse Fourier transform of the frequency response. So now if I take the complex conjugate of the function x of t, Then I also have to take the complex constant of the T, right? This is a real number, so it doesn't change. Okay? E is a real number, it doesn't change. Okay, so we have the x r of omega. And then the complex quantity of this complex exponential function is simply negative j omega t. Okay, and now here is the tricky part. If I change the frequency argument, I replace omega by negative omega prime. Let's change the variable, or change the argument, that's it. Change the dummy variable. Oh, sorry, this must be omega, so I'm going to mistake it. Oh, we did this mistake. Okay, sorry about this. So I change the dummy variable. I replace omega by negative omega prime. Just change the dummy variable. Okay? And this omega now is replaced by positive omega prime. And the omega now is replaced by the omega prime. Okay? And then we can, again, call the omega prime be negative omega. Just call it again. Okay? So now we have x of omega. And then you raise up the string on the space. Really, it's good as one. Maybe everything is up. Okay, so we can plan either get one. Make up one. Equals negative omega. So I have the omega prime equals negative omega. So the So the lower limit is omega. Then infinity. And then we carry the negative sign. Something not quite right without image, double check the thing. Okay. Give me a second, the image here. There is something here. This omega is the real function. Should not change. Sorry, let me figure this out next time. Sorry, I think I missed something here. I probably didn't forget to tell you. It's a little bit complicated. All right, sorry, I had to check that again. Sorry about that. Okay, so let me give you that out and tell you what happened here. Okay? So this is my mistake. Okay, one moment. So what I'm trying to say here is if we are dealing with a real function, similar to the Fourier series expansion, the magnitude will be symmetric. Okay, that's a real function. But the imaginary part will be an odd function as well. And here are some examples here. And let me show you the figure. So suppose I have a function x1 of t. Now this function is a real function. Now if you take the Fourier transform, you can see that the magnitude, okay, the first figure here is the magnitude of the Fourier transform is an even function. It is, sorry, let me work on the screen. So if we take the Fourier transform of this function, you can see that the magnitude, this is the magnitude of the Fourier transform. It's an even function centered at 0. Okay, so it is even function and centered at 0. But the phase angle or the imaginary part is an odd function. Okay, so this is the phase angle of the Fourier transform of x1 of t. And we have another function h2. Again, for this real function, if you take the Fourier transform, the magnitude is an even function, centered at 0. And the phase angle is an odd function, centered at 0 degrees per second, 0 degrees per second. Okay? Alright. Okay, I have to stop here. Okay, sorry about that. Let me figure that out. Okay, in the proof. I think I missed something here. I have to figure it out and then tell you the result next time. Okay? Sorry about that. And in the meantime, I will give you the slide again. Okay? So that you can take a look and read the contents. Alright? Okay, any questions before you leave? Question? Okay, I have a good evening and see you next time.